Recording started.
Okay, so we are going to talk about the difference between molecular compounds and ionic compounds. So an example of an ionic compound is salt, good old sodium chloride, table salt. That's an ionic compound. And molecular compounds, these are all different examples of them. Some of these are pretty common, like water, carbon dioxide, and so those are all molecular compounds. And you might have noticed in some of the names, like carbon dioxide, that they have things like di in them, right? Di or tri, that sort of thing. So those are called prefixes, right? And here's a table that shows different prefixes. So you can see if you have 2 atoms, it's di, 3 is tri, 4 is tetra, and so on, right? So with that in mind, what do you think the name would be for P2Cl3? What prefix do you think would go in this box, and which prefix do you think would go in that box? Okay, well, have a look and see, this is phosphorus, right? The P is phosphorus, and this tells us there's 2. So have a look on the table and see which prefix goes with the 2, and see which prefix goes with the 3, and tell me which one those are. Okay, so it's diphosphorus and trichloride. And remember, we changed the ending of the second name from chlorine to chloride, right? We always change its ending to IDE. Okay, so you want to be able to look at a compound like this and look up the P in the periodic table and see that that's phosphorus. Look up the Cl and see that that's chlorine. And so you want to be able to write this out as diphosphorus trichloride. Does that help a little bit? We'll go over some others as well. And again, please let me know if there's something you want to stop on, okay? All right, so now diphosphorus trichloride is a molecular compound. We already talked about that, right? Ionic compounds are different. Now, here's an example of an ionic compound. Now, the name of this ionic compound, it is calcium chloride. It's not calcium dichloride, okay? So when it's an ionic compound, you don't look at the subscript. These little numbers are called subscripts. You don't use the subscript in the name, okay? So again, it's not dichloride like it would be if it was a molecular compound. It's just calcium chloride, all right? So when that's what you do when it's an ionic compound. So again, only molecular compounds use the prefixes like di, tri, etc. Now, let's try to think about how we can tell, just by looking at the formula, whether it's an ionic or molecular compound. So let's just kind of review. Molecular compounds are made up of nonmetals plus nonmetals. Now, do you have your textbook with you right now that you could look on the periodic table? Okay, so nonmetals are always found on the right-hand side of the periodic table. And so an example would be, if you're looking at carbon dioxide, which is a molecular compound, it's made out of 2 nonmetals. First is carbon. Can you see carbon on the periodic table? And can you see oxygen? Okay, so they're kind of on the right-hand side of the periodic table, not the far right, but basically anything that's not the far left I wouldn't say anything, but the first two columns on the left are metals. The next ones are transition metals, but we don't usually deal with them as much when we're doing, you know, beginning chemistry sort of thing. Okay, so again, two nonmetals make up a molecular compound, and carbon dioxide is a molecular compound. Ionic compounds, on the other hand, are made of a metal joined to a nonmetal. Okay, so the metals are found on the left side of the table, and the nonmetals are found on the right-hand side of the table, like we already said. So if you look on your periodic table, you can see that the first element in sodium chloride, sodium is on the left side of the table, right? So it's a metal. And you can see that chlorine is on the right-hand side of the table. So again, you've got a metal plus a nonmetal when you've got an ionic compound. Okay, does that make sense? So again, molecular, nonmetal plus nonmetal, both on the right-hand side. Ionic compound, metal on the left plus nonmetal on the right. Okay, so let's just kind of test our knowledge of some of this stuff. So what kind of compounds are made of metal plus nonmetal? Good, right on. And the other compounds that are nonmetal plus nonmetal? Good, molecular, right on. All right, so let's go on to the next question. These kind of substances, these kind of elements are found on the left side of the periodic table, mostly columns 1 and 2. What would you say? Okay, metals, and the other one found on the right side of the periodic table would be, of course, nonmetals, right? Good. All right, so let's see if we can identify, in question 4, see if we can identify this compound here. What do you think? Thinking about the two kinds of elements that make up this compound, do you think this is an ionic or a molecular compound? Think about whether the first compound is a metal or a nonmetal in the second compound, and then compare that again to this stuff here. So what do you think? Okay, that's right. It's ionic because it's a metal plus a nonmetal. How about the next one? Yeah, good, right on. Okay, molecular. There we go. So with that in mind, thinking back to how we named molecular and ionic compounds, the differences there, what do you think the name of this first one would be? CaBr2. Okay, and when you put them together, what do you do to the ending of the second name whenever you combine two elements together? Okay, and do you think we have to worry at all about the 2, the subscript 2? Does that affect the naming at all? Remember, it only affects the naming if it's a molecular compound. If it's an ionic compound, then we don't worry about that too. So what do you think? Do we take that too into consideration with the name, or do we just ignore it? Yeah, we ignore it, that's right, because it's an ionic compound, right? And remember, just like calcium bromide, so again, remember, just like on the page before, when we had an ionic compound like this one right here, it was sodium chloride, and we didn't, actually it doesn't have any numbers in it, but we talked before, when we talked about calcium chloride and we said it was an ionic compound, we said it is not calcium dichloride because it's an ionic compound, right? So with that in mind, it is just calcium bromide. And how about the next one there? What do you think the name would be for that? Okay, and phosphorus. Now, do we have to worry about the 2 and the 3? Are they going to affect the name? Yep, they do, because it's a molecular compound, so we're going to have make it diphosphorus, and then it's going to be tri, because there's 3 bromines, tribromide. Okay, so again, because it's a molecular compound, because we have 2 nonmetals, we do pay attention to these subscripts. They do affect the name, and so this is di and this is tri. Does that make sense? Okay, good. So let's go on to the next page then. So here's a bit of a summary of what we've learned. Molecular compounds are made of nonmetals plus nonmetals, both found on the right-hand side of the table. So carbon and oxygen are both found on the right side, and carbon dioxide is a molecular compound. The name does tell you how many of each type of atom you have. So carbon dioxide does tell you that you have 2 oxygens. And we don't say anything for the 1 carbon. We don't say mono, carbon dioxide. We just do it when there's 2 or more. Okay, so carbon dioxide, because it's a molecular compound. Ionic compounds are made of metal from the left side, non-metal from the right side, like this here. And in this case, the name does not tell you how many of each atom you have. So in other words, the 2 doesn't affect the name when it's an ionic compound. So it's calcium chloride, it's not calcium dichloride. Okay, so that's just kind of a review. And we'll just kind of shift gears now. We're going to talk a little bit about what ionic compounds look like. So ionic compounds are what they call like kind of a crystal structure. And with a crystal structure, it's you've got this kind of grid network, if you know what I mean. Okay, so you've got these minus and plus charges that are in a grid network. They form a really rigid hard structure. And so this is Cl minus, and so that's the minus, and the Na plus is the plus. So you got 2 different charges, and that's what binds them together really strongly, an ionic compound. They're very strong compounds. So we know that electricity is the flow of charged particles, right? When you think about what electricity is, it's a bunch of negative electrons, okay? They have a negative charge, and they're flowing, they're moving, right? So since electricity is flowing, since it's the flow of electric charges or charged particles, electricity is going to flow better through ionic compounds. Why? Because they're made up of charged particles, right? So if electricity is about charged particles flowing, then it makes sense that if you've got a bunch of extra charged particles, that you're going to have more electricity, right? Okay, so electricity works better when you've got something like salt dissolved in water, an ionic compound dissolved in water. Okay, so salt is an ionic compound and it conducts electricity well. Sugar is a molecular compound and it does not conduct electricity well. Okay, so when we're talking about a compound that conducts electricity well, there's a name given to that type of compound. It's an electrolyte. Have you ever talked about electrolytes with maybe with hockey? Like if you're taking Gatorade or something like that? Does anyone ever say, you know, you got to drink some Gatorade because it'll replace your electrolytes? You ever heard anybody talk about that? Okay. Well, hey, and next time you do drink Gatorade, you know, it's got salt in it. And so that's why they're talking about that, because it's got electrolytes. It conducts electricity. So another thing that's kind of interesting is you've probably heard of lie detector tests, right? Well, the way those lie detector tests work is if a person's lying about something, they start getting nervous, and when they do, they start sweating, and sweat is made up of salt, right? So because you've got more salt happening, that conducts the electricity more. So if they've got some sort of electric thing, you know, strapped to your fingers or whatever, there's going to be more electricity flowing because you've got the salt coming out of your fingers from sweat, right? So that's kind of how a lie detector test works. All right, so let's just fill in the blanks for this one here. The first one, what kind of compounds are good electrolytes? Is it molecular or ionic? Okay, remember electrolytes have electricity. Which one of them, just thinking about their name, suggests that there's charged particles? Ionic or molecular? Well, it's actually ionic, right? Remember, because ions are charged particles. So ionic compounds have charged particles in them. Remember, we had the Na plus and the Cl minus, right? That was the ionic compound. It's the molecular compounds like sugar. They don't have charges, so they're not good electrolytes. Okay? All right, so we'll go on to the next page. And we're kind of shifting gears again. We're going to talk now at this point about pH. Now, you know, pH has to do with a lot of different important things in life. If you go to a swimming pool, maybe someone comes by and they do a test while you're swimming in the pool. They want to make sure that the pH of the pool is okay. I don't know if you've ever seen that before. And then if you talk about things like your shampoo has to be the right pH. I'm not sure if it shows it here. What the pH of shampoo is. Anyways, of course we know that acids are low pH, bases are a high pH, but another thing, we're going to talk about how water has both H plus and O minus ions. Okay, so what's this business about H plus and O minus ions? Well, H plus ions are found in acids. Okay, so when you put an acid in water, it produces all these little H pluses, right? There might be a few O minuses, but it's mostly H pluses, okay? So then you're going to have a low pH. Now, if there's a lot of O minuses, that's a base, okay? So H plus is an acid, O minus is a base. Now, if you have water, water is not an acid and it's not a base. It's neutral. It's right in between the two. Its pH is 7, right? So because of that, it has equal amounts of H plus and O minus in water. Okay? So now we're going to talk about something else, and in a minute, just a minute, I'm going to put a little movie on here. But facilitated diffusion, what is that? Okay, facilitated diffusion involves membrane proteins. Okay, so you remember you have this membrane that's around the outside of the cell. It lets things in and out of the cell. So before we talk about what facilitated diffusion is, let's remind ourselves what diffusion is. Okay? So diffusion is the movement of particles from where they are in high concentration, in other words, lots of them, to where they are in low concentration. Okay? So like this here, there's a lot of particles. That's high concentration. This side has low concentration of particles. So the particles are going to move to this side. That's diffusion. And again, it just happens naturally because the particles bump into each other, and as they bump into each other, they spread out, and they just naturally spread out more and more. It's like if you go to a movie theater, First of all, the smell is near the place where they, if they make some popcorn, it's near where they produce the popcorn. But those smell particles bump into each other more and more, and they spread out throughout the whole movie theater. Okay? So that's diffusion. So after they've spread out, this is what you get, an equal concentration. Okay? That shows diffusion has taken place. So that's normal diffusion. But when we talk about facilitated diffusion, we're going to see it's something else. Okay, so what does this word facilitate mean? Facilitate means to help something happen. So you might have a facilitator in a meeting like this guy is, and what he does is he helps the meeting, go along smoothly. If this is a counseling session or whatever, it's a person who, brings the people together and helps everything go smoothly. Okay, so a facilitator is someone who helps something to happen. And so when we talk about facilitated diffusion, we're going to see that these proteins help something happen. Okay? So I'm just going to get the link that you see below here. I'm going to paste it into the chat box. It looks like I just got kicked off of school. You know how it is if you haven't done something for a little while, it kind of kicks you out. So I just have to get back on and get this first link. Then I will post it. And so if you just want to let me know once you've watched that, and then we'll get going again. I'll just quickly say while you're watching that, take note of what happens to the protein whenever something passes through it. Okay, good. So did you notice what happened to the protein every time something went through it? Okay, so the thing is transferred from one side to the other, and if you think about what happens to the protein moved and changed its shape each time to let the thing pass through, right? If you look at this here, you can see how this is kind of changing its shape, right? It's like this, but then it goes like that, so it's changing its shape. So I wrote down here, with facilitated diffusion, a carrier protein changes shape, which helps to move the molecules into the cell. And now how does it work? Well, the way it works is, and I think it might have shown this in the video, I think the molecules that went through, they had different shapes as well, right? So based on the shape of the molecules, that changed the shape of the protein, right? It caused it to change. The shape of the molecules caused the protein to change. Now also the electrical charge of these molecules could also affect this protein. Okay, so those are the two things about the molecules that affect the protein. Alright, so just a question then. What happens to the carrier protein which allows molecules to move into the cell during facilitated diffusion? What is it that changes about that protein? Okay, good, awesome. And then which two things are true about the molecules which pass through the proteins, which allow them to pass through? Okay, remember it's the shape and the electrical charge. Okay? Alright, so let's go on to the next page then. We're going to talk about a dynamic equilibrium. Okay? So when with a dynamic equilibrium, molecules are moving back and forth, but the amount that you have on both sides is equal. Okay? So what we're going to do is we're going to look at each part of those words, dynamic equilibrium. Okay? We're going to look at equilibrium and then dynamic. So let's see what that means. Well, equilibrium means that everything's in balance. It means that you have the same amount on both sides. It means that everything's spread out. Okay? So that's what equilibrium is. That's when you have the same concentration of molecules on both sides. So that's what you get after diffusion has taken place. That's an equilibrium, right? Now, if you had a situation where all these molecules were just staying there, that would be just an equilibrium. But if we're talking about a dynamic equilibrium, which is usually what happens, what does the word dynamic mean? Well, dynamic means that something's moving. You might have heard of like a dynamic speaker or something like that. Someone who kind of moves all over the place on the stage and they're moving their hands all over the place. You know, they're moving, right? Okay, so this is a dynamic equilibrium because molecules are moving back and forth, even though it just looks like there's the same amount always on both sides. The amount on both sides isn't changing, but the molecules are moving back and forth. Okay, so that's why it's a dynamic equilibrium, because they're moving, they're not just staying there. Okay? So that's what we mean by a dynamic equilibrium. Okay, so what does equilibrium mean? Okay, how about I'll answer this one. Equilibrium kind of means balance, right? The left and right side are balanced. And what does the word dynamic mean again? Okay, you remember dynamic means moving, right? The molecules are still moving from side to side. So, hey, I was wondering, do you want to take just a break for a bit and get a drink or something like that, or do you want to keep going? Okay, sure. So yeah, just let me know when you're back and we'll go from there. Please don't come in. I'm doing this. Well, that's good. Hey, why not, eh? While you were gone, my son was coming into the room here, and he had all this goalie equipment on. It was kind of funny. I think he was playing goalie with my other son, or hockey with my other son. I think I have to try to resurface my driveway or something like that, because you know, sometimes when you're on a surface where it's not very flat and you're trying to do stick work, you know, like back and forth, and it's just not, it's hard to do it on certain surfaces, and that's kind of how our driveway is. So I think I need to resurface it at some point. Anyways, our kids really like playing floor hockey, or road hockey, whatever. So, all right, so let's get going on this again. We're going to talk about what happens at a phase change. And what happens during a phase change, the amount of heat changes, but there's no change in temperature. Okay? And that might sound kind of weird. What do we mean? Heat changes, but temperature doesn't change. And also, what is a phase change anyways? Well, a phase change is every time you go from something like a solid to a liquid, or a liquid to a gas. Okay? Each one of those are different phases, right? So a solid's one phase, liquid's another, and gas is another, right? And so, for instance, if you have a solid going to a liquid, that's melting. You go from a liquid to a gas, that's evaporation. But the important thing to know is that there's no temperature change at the moment when you go from one to the other. Okay? Now, I know the temperature does change eventually. Like, for instance, here you have a solid. Here you have a solid, and here you have a solid liquid, right? And so during this period, there's no temperature change, right? Okay? So there's no temperature change going from a solid to a liquid. Now, eventually there will be one later on, but there's none right away. Okay? So I just wrote down here, going from a solid to a liquid, heat is moving. Okay? Heat goes into the solid, but the temperature change is none. If you're going from a liquid to a solid, again, heat leaves the liquid as it freezes. But again, the temperature change is none at that moment anyways, right? Going from a liquid to a gas, again, heat is changing, but the temperature is not going up or down at that moment, okay? So just remember that during a phase change, there's no change in temperature. A bit afterwards, the temperature does go up, but not right away. Okay, so I just have a blank here. When a phase change happens, there's a change in the amount of what, but not in the amount of something else. So what goes in the first blank? What goes in the second blank? Do you know which would go in either one of those blanks? Okay, well again, if we look at this chart, we see there is a change in the amount of heat, right? But there's no change in temperature, okay? So we would say there's a change in the amount of heat, but not in the temperature. Okay, because heat is just the transfer of energy, right? But temperature is when it's actually going up. Okay, so do you remember we talked about heat capacities before? Like some types of substances, their temperature changes more when you add heat to them, and some it doesn't change as much. Okay? So if you look at this one here, you can see if you add the same amount of heat to both these two substances, this one goes up all the way to 90 degrees Celsius, gold, right? Whereas if you add the same amount of heat to aluminum, it doesn't change very much. That's why some people make engines out of aluminum, okay, because the temperature doesn't go up very much. All right? So what you could say is you could say that the same amount of heat energy that's given to both the gold and the aluminum results in a different temperature rise. Okay, greater temperature rise, smaller temperature rise. Okay, same amount of energy, different rise in temperature. Or another way of looking at it is you would have to add different amounts of heat to get the same rise in temperature. Okay, so for instance, you might only need to add a little bit of heat to get the same rise in temperature as this one. You would need to add more heat if you wanted to have the temperature rise the same. Okay, so looking at that then, so when we think about what goes in this blank here, when two substances have different heat capacities, the amount of heat energy we add to the two substances would be different from the amount of temperature we get out of them. Okay? So we get different temperatures. And we saw that, right, in the diagram? Okay, so this here, we kind of talked about this earlier. If you do work on an object, it increases its mechanical energy. Okay, so what does that mean? Well, if a golfer is swinging a golf club, he's doing work on the club, right? Okay, he's giving energy to that club. Then the club hits the ball, so the club does work on the ball, right? Okay, so again, doing work increases mechanical energy. That's the kind of energy, okay? And when we talk about mechanical energy, it's made up of two types. There's kinetic energy, which is moving energy, and there's stored energy, potential energy, okay? But those two types together are both types of mechanical energy, okay? So again, doing work on an object increases the amount of its mechanical energy, okay? That's the type of energy. All right, so now we're going to look at, you remember before we talked about work equals force times distance, and you remember we looked at a diagram, we looked at a situation where someone was pushing on a box or pushing on a fridge, and they were pushing with all their might, but even though they were pushing with all their might, if the fridge didn't move, according to science, they weren't actually doing any work on it. Do you kind of remember us talking about that before? I don't know, like maybe a week ago or so, okay? Now the reason that was because work equals force times distance, and if you have force, if you're pushing on the fridge with force, but you don't move it, there's no distance, you haven't done any work, okay? So work equals force times distance. So to solve this problem here, we're going to have to use that formula. Okay, so we've got a wind, and we've got it expressed in two different speeds, kilometers per hour and meters per second. It's blowing towards a sailboat, and it creates a force of 3.2 newtons on the sail. It's strong enough to push a 0.5 kilogram boat a distance of 13.2 meters. And it says how much work does the wind do on the sailboat? Okay, so we want to find work, so we want to multiply force times distance. If you look at this problem here, there's a lot of numbers in it, eh? But the good thing is, we just need to pick out the ones that are force and distance. Okay? Do you remember what units we measure force in? Actually, you're close. That's work or energy. Both work and energy are measured in joules. Force is measured in newtons, which we have the letter N stand for. Okay? So if you read the problem there, can you tell me how many newtons of force are being applied to the sail from the wind? Okay, 3.2. So first of all, let's write work equals force times distance, just so we've got our formula there. Underneath force, we write 3.2 newtons. And what's the distance? Okay, 13.2 meters, good. And so we would just multiply those two together. I'm not going to even bother to do that. That's pretty easy. But you can see how we were able to pick out the numbers. And we didn't, there were a lot of numbers like kilometers per hour, meters per second. They didn't even apply, right? Because the only thing that applies is force times distance when you're talking about work. So that's a good thing. All right, now we're going to look again at, remember acceleration is velocity divided by time. Do you remember acceleration is when something's going faster and faster, right? If you have constant acceleration, it's like gravity. Everything that drops on the Earth drops at 9.8 meters per second squared. That means every second it goes 9.8 meters per second faster, right? And the cool thing is, even if it's a piano or it's a little tiny marble or tiny pea, they both hit the ground at the same time, right? Because gravity accelerates all objects at the same rate. The only thing that would be different is if you had something like a Kleenex, then it wouldn't be at the same rate, because then you've got like air resistance and it kind of floats, so that's a little bit different. So anyways, okay, so acceleration is change in velocity divided by change in time. So we're going to use that formula, but the thing is, if we read this question, it says, after 5 seconds, how fast is the marble moving? Okay? Now when it's talking about how fast it is, remember that's going to be velocity, or speed, right? So we want to find velocity. So we got to use this formula, but we got to switch it around so we can have velocity equals something else. So how do we do that? Well, we could do it in different ways if we want to just get velocity on the right-hand side. Since we have velocity divided by time, remember the opposite of divided by time is times time. So we multiply both sides of the equation by time. Okay? When we do that, time is on top and bottom. It cancels out. So I'm just gonna draw that for you. It cancels out. And what that means is we're left with velocity on the right-hand side by itself. So velocity equals acceleration times time. And that's great now. Now we have the formula for velocity, and that's what we want to find. So all we need to do is plug in the acceleration from the question, 9.8, underneath acceleration, underneath time, plug in 5 seconds, and so we multiply 9.8 times 5, and we get this as an answer. Okay? So that's how we found velocity. So again, we need to know this formula and know how to be able to switch it around to find velocity instead of acceleration. Okay? Is that one cool? Okay, good. So going on to the next page, we're kind of moving away from the equations right now. We're going to talk about something called spontaneous generation. So years ago, people used to think that you could have non-living things come from living, or living things come from non-living things, okay? And that was called spontaneous generation. So generation is like when something's produced, and spontaneous is, you know, just kind of out of the blue sort of thing. Okay, so something being produced just out of the blue. So, for instance, the theory of spontaneous generation would say that flies could come from meat. Okay, so basically just meat by itself would just produce flies. That was the original thinking that people had. So they did a test to see whether or not spontaneous generation was true or false. So if it was true, then flies just came right out of the meat. Nothing else was involved. If it was false, then flies only came from other flies. Okay? So I bet you've already got a good idea about which was true. But back then, they didn't have, you know, it wasn't so clear to them which was true, right? So what we're going to do then, we're just going to quickly watch a little video, short video about spontaneous generation. And so I just have to find that video and then I'll put it up. Just give me a sec here. Okay, so again, just let me know when you're done. Okay, good stuff. I don't know if you hear in the background, there's a lot of rain coming against my window there. I don't know if that gets picked up on the microphone there. Anyways, just going to quickly go over the different results, and just a kind of reminder, you probably saw at least some of the stuff when you watched the video. So you had, first of all, you had a sealed flask, and so it was totally sealed, and so because of that, they observed there were no flies or eggs that were able to enter. That's what they observed with their eyes. What their conclusion was there were no flies that were seen because no flies could enter, right? Or eggs could enter. Now there also was a situation where you had some gauze, so it wasn't completely blocked off. It was kind of like, kind of like a mesh screen sort of thing, right? Now in this situation, what they observed, they saw flies laying their eggs on the gauze, right? Then what would happen is the eggs would drop through, and so some of them were then found on the meat. So in this one here, they found eggs or maggots, the little crawling guys, on the meat, right? This last one was open, so the flies could enter. And because the flies could enter, they laid what they saw them, this is their observation, they saw them entering, they saw them laying their eggs on the meat, and their conclusion was that the maggots, the baby flies, hatched from the eggs and grew into new flies. Okay? So, the question then, was the theory of spontaneous generation proven true, or was it proven false? What do you think? Okay. Let's take a look at this section here. That's right. So they only came from other flies, but they came from the eggs that were laid from other flies, right? So it is false. Spontaneous generation says that flies only came from the meat, but they came from other flies because they came from the eggs that came from other flies, right? So spontaneous generation was proven false. Does that make sense? Okay. And the other thing I think about when I think about this is that to me it's also suggests that that there's a God, because the idea that living things could just all of a sudden come out of nowhere, to me it suggests that there's a God who created everything. So to me that kind of goes against spontaneous generation, the idea that the life that we see on Earth would have just come here, on its own, without God creating it. All right, so we're actually going to, at this point, we've finished all the stuff that kind of focuses on the final exam. So the recording and the PDF file I made a few days ago, and and this one here, what we've done up to this point kind of covers all the stuff. Like I, kind of went through the questions on the final exam and wrote all that stuff so far. Okay, so I just wanted to mention that the stuff we're going to cover at this point kind of covers the stuff from assignment 17. Okay, so I wasn't sure exactly which stuff you wanted to cover from assignment 17, but I think I might know some of the things that might be things that you might need a little more explanation on. I don't know, do you want me to go over, what the biomes are and, what the different biomes are, or do you feel like you know that pretty well? Okay. All right, so biomes, again, are large areas of the world where you have climate, plants, and animals that are the same, okay? So for instance, if you're talking about the tundra biome, in the tundra biome, you always have a certain type of climate, a certain type of plants, a certain type of animals living there, right? So looking at the different types of biomes, and we'll look at a diagram in a sec, in places like Africa, you have savanna, where there's moderate rainfall and a long dry season, okay? And the plants that are found there are mainly grasses, and animals are primarily grazing animals like gazelles. Okay, so if you think of something like the Lion King movie, that takes place in the savannah, a lot of it, okay? Like you see a lot of grasses and stuff like that. Now the desert, of course, is very dry, and because it's dry, you have plants and animals that are adapted, so they're specially made in ways that help them survive in dry conditions. For instance, you have leaves that have kind of a waxy coating on them, and the waxy coating means they don't lose water as much, which is good because they need all the water they can have because it's so dry, right? On the other hand, with deserts, we know that it gets really hot during the day, cold at night, so animals are made to burrow so they avoid the heat, right? Okay, how about scrub forests? Well, those are found in maritime climates that don't have very much rain in the summer, and so because of that, the plants are resistant to drought. Okay, so they're made in such a way that they can put up with the drought. Coniferous forests, okay, remember there's two different types of trees, right? Trees like maple leaf trees are deciduous trees. Conifer trees are cone-bearing trees, such as spruce or pine, okay? So those are the kinds you find in coniferous forests. In these places, winters are cold and wet, and summers are short and dry. And then there's the tundra, right? The tundra is found near the Arctic, and it's very dry there. And the ground is permanently frozen all year round, and because of that, we call it permafrost. Okay? So those are some of the main biomes. And here's just a picture of some of them. And just wanted to make note, this is the tundra. And remember, the tundra is only really found in the Arctic, the northern hemisphere. It's not found in the southern hemisphere. All right. So there's just a picture of some of the different biomes. And okay, so we're going to go from biomes. We're going to talk about positive and negative feedback systems. And I'm guessing this might have been an area that you'd like a little more explanation on from lesson 17. So what's the difference between positive feedback and negative feedback? Okay, positive feedback is like when you put money in the bank. Okay, so if I go down to the bank, I put $100 in there, I get interest. Okay, so now I have, let's say I have $5 that I made in interest that year. Now I have 105. So guess what? The next year I'm going to have more interest because I had $105 that I got interest on. I didn't just have $100, so I got even more interest. Okay, so my account grows more and more. Okay, I get interest on my interest. That's called positive feedback, when something grows more and more and more and more. Okay, negative feedback is a different situation. With negative feedback, there's something happens that causes it to just stop. It discontinues. So an example is, let's say your body temperature rises. Let's say you're playing lots of hockey, for instance. What happens? Well, you sweat more, right? When you sweat more, it causes you to cool down, right? Okay? So in other words, it stops your body from temperature from rising, so the whole thing just stops. It doesn't grow more and more, it stops. So that's negative feedback. Okay? So I just put down a positive feedback system feeds on itself, it grows more and more, whereas a negative feedback system shuts itself down. All right, so now that we've got kind of a basic idea about that, let's see how that involves the climate and things like water vapor. So let's look at an example of positive water vapor feedback. Okay, so basically it's a type of positive feedback. So we know it's going to build on itself. There's going to be something happening where something happens more and more. So what happens here is you have water up in the atmosphere, okay? And water is like a greenhouse gas, right? Remember what happens with those greenhouse gases. What happens is the light passes through a greenhouse, but inside the greenhouse it turns into heat energy and then it gets trapped inside the greenhouse. It can't pass through. Same thing with water vapors, same thing with carbon dioxide. Okay? When they go up in the atmosphere, the light passes through, but it can't, once it hits the earth, it turns to heat and it can't leave. Okay? So heat gets trapped. So the reason why this is a positive system that feeds on itself, you have this water vapor and it traps the heat. So because it traps the heat in the atmosphere, the water vapor in the atmosphere, well, the temperatures go up, and because the temperature goes up, warm air is able to hold more heat. So because of that, the warm air is holding even more heat, and so that means there's more water vapor in the atmosphere, because water vapor, the more heat there is, the more water vapor there can be in the atmosphere. Okay? So you get even more water vapor because the air was heated up, and so because of that, you get even more global warming, and it goes more and more. Okay, so water vapor leads to high temperature in the atmosphere, which leads to more water vapor. Okay, so that's a positive feedback system. Negative feedback system, again, something happens that shuts it down. So what happens here is the idea is that you've got clouds in the sky, and because you've got clouds, the light gets blocked. So because it gets blocked, things get cooler. Okay? So this time, instead of getting warmer and warmer, things get cooler. Okay, so that's a negative feedback system. Things are shutting down. Now, the funny thing is that both the positive and the negative feedback system include water vapor, right? In the positive system, the water vapor is making things warmer and warmer. In the negative feedback system, the water vapor, which is what clouds are really made of, right? It makes things colder. So what's really going on in our environment? Well, you know what? Scientists really don't know totally. And, you know, because some of them think that, you know, we've got negative feedback going on, some of them think positive feedback, and a lot of them think that both is going on depending on how high the clouds are. So anyways, that's just showing the difference between positive and negative feedback. Positive feedback, something builds on itself more and more. Negative feedback, something causes the system to shut down. All right? And just to go into a little bit more depth of what the greenhouse system's all about again. So again, remember, both water and carbon dioxide are greenhouse gases. Sometimes people think it's just carbon dioxide, but even water is considered a greenhouse gas. Okay, so you've got these gases up in our atmosphere, and again, what happens is the light passes through them, but when it hits the Earth, light waves are changed into heat waves. But heat waves are a longer type of wave, and they're not able to pass through this barrier of the gases. The gases is like a barrier. So the light can pass through the gas barrier. The heat waves cannot pass through the barrier. They get trapped inside our atmosphere, and so things get warmer and warmer. And that's the concern people have about, you know, that there's carbon dioxide, you know, from cars and industries and stuff like that, making things warmer and warmer. And part of the concern is they say that, you know, we're not really cutting down on these things. Things are maybe even increasing, like the trucks and the transport industry and that kind of thing, that there's more and more of it. Okay? So the greenhouse effect, over time, some people think that it will lead to global warming. Right? And, you know, this is possible, I think. I also think it's, you know, something that we probably, you know, we need to be careful about, but, you know, we just do our best, really. That's all we can do, right? And leave the rest up to God. So that's the greenhouse effect and global warming. And again, remember, both carbon dioxide and water vapor can be a greenhouse gas. All right, so I'm going to stop the recording now, and I guess I'll just a reminder that both these two recordings here, you know, the stuff I've gone over is what's going to be on the final exam. So, you know, watching these recordings, making notes from them, and also practicing stuff on the PDF files, that'll help you do well on the final.